Imagine setting up a line of dominoes. You knock the first one over, and it falls exactly as you expect. Then the second, the third, the thousandth. But what happens when that flawlessly repeating sequence comes to a sudden, jarring stop? Our brains rely on inductive reasoning. We observe specific events, the sun rising every morning, or a sequence of numbers doubling, and we naturally assume that because it happened repeatedly, it must be a universal law. This is where we run into a formal mathematical warning known as the strong law of small numbers. It is a principle that explains why our pattern-hungry minds get repeatedly tricked by numerical coincidences. The core of this law is simple. There are only so many small integers available to represent the infinite demands we make of them. Because the pool of early numbers is so limited, certain sequences are bound to overlap and mimic each other by pure chance. Our biology makes it difficult to distinguish a strong coincidence from a universal law. When we see a pattern hold for the first dozen steps, we instinctively stop looking for the moment it might fail. Look at this geometric sequence. If you place points on the circumference of a circle and connect them, the number of divided regions seems to follow a doubling pattern: 1, 2, 4, 8, 16. Naturally, we expect the next step to yield 32, but it doesn't. Connect 6 points and the circle divides into exactly 31 regions. That initial regularity hijacked our logic, leading us straight into a false assumption. This trap scales up to massive proportions. Take the Pólya conjecture of 1919. It hypothesized that if you factor natural numbers into their constituent primes, most of them will have an odd number of prime factors. For decades, every single number tested supported the conjecture, but eventually the streak ended. At the scale of 906,150,257, the pattern experiences a sudden shift, and numbers with an even amount of prime factors overtake the odd. Or consider the Borwein integral, a complex calculus operation that calculates perfectly to pi divided by 2. It holds for the first 14 iterations, and then abruptly shatters at the 15th step, dropping off by a fraction of a decimal. Observation is the starting point for every great discovery, but it isn't the finish line. In mathematics, a billion successful examples can suggest a truth, but they cannot establish it with the absolute necessity required for a proof. No problem exploits this gap between evidence and truth quite like the Collatz conjecture. It is a deceptively simple trap that has consumed generations of mathematicians who find it impossible to prove what seems obvious. The rules are elementary. Pick any positive integer. If it's even, divide it by 2. If it's odd, triple it and add 1. Repeat those two operations, and every tap appears to lead to an inescapable loop, funneling back to 1. We have used supercomputers to verify quintillions of paths. Every single starting number we check behaves exactly the same way, crashing back to 1 without a single exception. Recently, Terence made a breakthrough, proving that almost all starting numbers will eventually reach restricted, bounded values. He successfully cornered the problem using probabilistic methods. But because we are dealing with an infinite set of integers, almost all is still a shortfall. There is always the possibility that a single, undiscovered number out there deviates from the rule and diverges toward infinity. We see a similar standoff with the twin prime conjecture. Prime numbers, those divisible only by 1 and themselves, occasionally appear in pairs separated by a gap of 2, like 11 and 13. Computational models and supercomputer runs suggest that these twin primes continue appearing forever. But the strong law of small numbers reminds us that even an endless-looking repetition might be a massive coincidence. In 2013, mathematician Zhang found a way to bypass the computational trap. He proved that you will infinitely often find prime pairs separated by a bounded gap, helping us compress that distance down from infinity to a maximum of 70 million. Soon after, the polymath project tightened Zhang's work even further. They reduced the boundary space until they could prove that infinite pairs exist within a gap of just 246. Yet, even though these breakthroughs corral the infinite into a tightly managed boundary, we are still short of the exact gap of 2. The definitive proof remains out of reach. Ultimately, mathematicians must navigate a strict divide. They must choose between intuition, the feeling a pattern is true, and the rigorous demands of logic. This is tied to decidability. To truly solve a mathematical problem, we cannot rely on observation. We have to build a deductive proof, deriving the conclusion step by step from foundational axioms, the universally accepted starting rules of mathematics. This is why mathematical deduction is irrefutable. Instead of guessing rules from observations, it applies overarching laws to move toward a conclusion with strict necessity. Logic must transcend what we can see or calculate. In this field, being 99.9% sure is an admission that the final link in the chain is still missing. Until a mathematician maps the logic required to reach the end of infinity, these conjectures remain incomplete. They are predictions that work in practice, but lack the formal scaffolding required to be called a law.